Okay, now we're going to put it all together. All of the algebra and all the calculus learned. This theory behind this section on curve sketching is that if you understand the algebra and calculus of curves, you don't need a graphing calculator or a graphing utility to sketch a function. So let's look at some of the things we're going to talk about. Now, from algebra, you knew about x and y intercepts, symmetry, domain, and range. We talked about continuity, asymptotes, differentiability, extrema, concavity, horizontal asymptotes, slant asymptotes, and so forth. So basically, we want to get as much of the information above as possible and use that to sketch the graph without using technology. Okay, so let's start with a simple polynomial function. So this polynomial function is 3x to the fifth minus 5x cubed. So let's talk about the intercepts. So you kind of have to watch this to see how I've got this structured. The intercepts. Well, if you let x be 0, then you're going to get y equals 0. So 0, 0 is a point on the graph, and that's actually a x and a y intercept. Now, if you let y be 0 and solve for x, you're actually going to get, you can factor x cubed out of that, and then you get 3x squared minus 5, and you get x cubed equals 0, which leads to x equals 0, which we already knew. But if you solve this equation, you actually get x equals plus or minus the square root of 5/3, which is roughly plus or minus 1.9. Now, I never said that these were going to be nice round numbers. Now, if you evaluate the function at negative x, you'll actually get minus f of x. So that tells us it's an odd function, so it's symmetric with respect to the origin. Since it's a polynomial, its domain is all real numbers and range is all real numbers, and it's continuous throughout its domain. And we already talked about the intercepts. Okay, we're not going to have asymptotes on polynomial functions, so we can skip that. Now let's talk about increasing, decreasing, and extrema. So I'm going to do the work over here. Here's the derivative, 15x to the fourth minus 15x squared. Factor 15x squared out, and I get 15x squared times x squared minus 1. So if I solve that for the critical numbers, I get 0 and plus or minus 1. Now, if I do the second derivative test on those numbers, I'll find that the second derivative at negative 1 is a negative number, so I get a max. I get a max at f of negative 1 of 2. And then if I evaluate second derivative at positive 1, it's a positive number, so I'm going to get a min at f of 1, and that's going to be negative 2. The second derivative test fails at 0. But if you do the first derivative test, you'll find that you don't get an extrema at that point. Now, if you test your intervals, which I didn't do here, but you know how to do that, so test your intervals around negative 1 and 1, you'll find that the function's increasing on negative infinity to negative 1 and on 1 to infinity, and the function is decreasing from negative 1 to 1. And as I said over here, your points that represent your relative extrema are the points negative 1, 2, and 1, negative 2. Okay, now let's talk about concavity. Okay, so we need the second derivative. So over here I got the second derivative. I factored it, so I got factored 30x out, and I got 2x squared minus 1. Well, that means x equals 0 is a possible point of inflection. But if I solve this equation, set 2x squared minus 1 equals 0, solve it, then I'll get x equals plus or minus the square root of a half, which is actually plus or minus 0.71. So let's test let's think about what would be less than negative 0.71. Negative 1. So the second derivative is negative to the left of negative 0.71, which is negative square root of a half. So we're concave down in that interval. Now, between negative 0.71 and 0, I have negative 0.5. If I put negative 0.5 back into the second derivative, I got a positive number, so it's concave up on that interval. And then just to the right, between 0 and positive square root of a half, is actually that should be positive 0.5. It's positive 0.5. And so I got a negative there, so it's concave down on that interval. And then a number to the right of square root of a half is 1. And so when I plug that in, I got a positive second derivative, so it's concave up on that interval. So putting all that together, it's concave down on these intervals, and it's concave up on that interval. And I have no idea what that is, but anyway, the point of inflections are minus square root of a half, 0, and plus square root of a half. Now, to get the corresponding y values for these numbers, I actually had to go back to the original function and plug in minus square root of a half and plus square root of a half. But one thing that's helpful is I know since it's an odd function, then when I put minus square root of a half in and I get this number, then plus square root of a half is going to give me the opposite of that number. So that's something from about an odd function that's helpful. So what I need you to do as far as graphing, I need you to pretend like you don't see the graph yet. Okay, can you do that? Alright, now I'm going to identify the intercept. Here's the x-intercept, and also had an intercept here that's also an x and y-intercept. Okay, now I identified the extrema points in blue. So negative 1, 2 is an extreme value, and 1, negative 2 is an extreme value. And I used green points here to identify where the points of inflection were. I had 3 points of inflection. So those are the points of inflection. And this just needs to go away. If I can get rid of it. There we go. Alright, so actually, if you go back and look at the information, you'll see that the function was increasing to negative 1. Then from negative 1 to 1 it was decreasing. Then from 1 to infinity it was increasing. So here you can see the function's got to be increasing, so you draw the function to go through this intercept and increasing. And also it's concave down on this interval, and it maxes out here, and it continues concave down until you get to minus square root of a half, which is right here. Okay, then it switches to concave up, but it's decreasing now. Remember, it's decreasing from negative 1 to 0, actually negative 1 to 1. So it's decreasing, and it's concave down. Then it switches to concave up, and then at 0 it changes from concave up back to concave down. And then at positive square root of a half here, it changes back to concave up. And at 1, it switches from decreasing to increasing, and then it goes through this other point, which I forgot to label, but that's the other x-intercept. I forgot, what was that? Those were what, plus or minus the square root of 5/3 or something like that? So anyway, once you get the intercepts, the extrema, the points of inflection, and then you can use the concept of increasing, decreasing, and concavity to piece the function together. Okay, now here's a rational function, and if you set this equal to 0, you get x equals plus or minus 3. And if you let x equal 0, which I don't think I did here, yeah, I did. If you let x equal 0, you get positive 9/2. So if you let x equal 0, you're going to get negative 18 over negative 4, which reduces to 9/2. So that's your intercepts. the domain is negative infinity to negative 2 union negative 2 to 2 union 2 to infinity, because x can't be plus or minus 2. And this is an even function, so it's symmetric with respect to the y-axis. And I didn't mention that on the last one. See how this is symmetric across the origin? So across the origin here, you've got basically an identical picture. It's just kind of flipped the other way. Okay, well this is an even function, so it's going to have symmetry with respect to the y-axis. Well, the asymptotes, you can see that the degree of the top and the degree of the bottom are the same, so 2 over 1 would be the horizontal asymptote, so y equal 2 is the horizontal asymptote. And then plus or minus 2 makes the denominator 0, so those are going to be vertical asymptotes. And then if you get the second derivative is 0 at 0, so x equals 0 is a critical number. But I also want to look at it around the vertical asymptotes. So basically I broke the x-axis up at negative 2, 0, and positive 2. And I'll just kind of summarize this because you know how to do this. I tested the numbers in each interval and I determined whether the first derivative was positive or negative. And based on those results, I've determined that the function is increasing on 0 to 2 and 2 to infinity, and it's decreasing on negative infinity to negative 2 and negative 2 to 0. And then I only had one extrema, and that's at negative 9/2, and that's a relative min. And then when I tested for concavity, the second derivative, there's no way that this can be 0. Since this cannot equal 0, I can't get any points of inflection. But I'm still going to check concavity on each side of the vertical asymptotes. So I'm going to test the second derivative in each of these intervals here to check for concavity. So based on those results, the second derivative is negative here, positive here, negative here. So it's concave down on the two outer regions, and then it's concave up on the inner region. And then after that, we want to try to piece this together. So first things first, let's identify our intercepts. We have an intercept here at 3 and minus 3, and we have a y-intercept here at 0 and 9/2. Now that point 0 and 9/2 is also a minimum. Okay, now we know that x equal 2, these two green lines, or x equal plus or minus 2, are vertical asymptotes, and we know that y equal 2, the horizontal line, is a horizontal asymptote. Okay, well, if you were to plot some other points, it might be helpful, but in order for this graph to go through this point, and for this line to be a vertical asymptote and this line to be a horizontal asymptote, it makes sense, and especially since the graph is decreasing and concave down over here, then it makes sense that it's going to look like that over here. And then on this side, the graph is increasing and concave down, and it's got to go through this point, so it makes sense for this to be the vertical asymptote. It's got to be getting close to this, it's got to be going down as you get close to it, and then as you come up and go out to infinity, it should get closer and closer to that horizontal asymptote. And then in here, the graph was concave up, and since this is a minimum, it must be coming down and then turning around and going back up. And so there's the graph of that one. Now on the next video, I'll go ahead and sketch a graph that involves a radical and a graph that involves a trig function. And then we'll be finished with the curve sketching aspect.